Good afternoon, everyone. I am Pranay, and I'll be handling the hands-on session right now. The current case which we are going to solve using OpenFOAM is the classic sawtube case. The sawtube is basically a device which we'll study ahead, but I'll tell you the main purpose of it. It is basically used to understand how high pressure waves, how shock waves, which are created when there is discontinuity in the pressure due to abrupt changes. Consider a shock wave to the two images shown in the slide. The left one, the fighter jet one, it comes at all the shock waves here are coming at above supersonic speeds, like above Mach 1. What happens is, as the speed increases, the local velocity of sound increases, and the local speed increases than the velocity of the sound, in fact. And this changes is transferred in the form of a shock wave. Or and the shock wave is more of a discontinuity thing. The discontinuity is transferred via pressure, can be is observed in density, is observed in temperature and velocity. As you can see in the graph, the pressure can rise, the pressure rises, density decreases, temperature increases, and the velocity decreases. So, as speaking, shock waves are a phenomena occurring due to changes in pressure, velocity, density, etc. And it is not only observed in external flow at very high speeds, but also you can mimic it by during blast waves, during testing of ammunition bombs. We might relate to it while watching movie Parmanu. During the last climax part, during the testing, we can see the blast waves. Blast waves were being felt by the people behind the window. So that is the intensity of shock wave on a large scale. But even on a smaller scale, when fighter jets cruises by, we feel the thundering rage of it in our body. We shiver it, we feel it. So basically, in open form, now comes that is what we are trying to do in open form is trying to mimic it and understand how shock waves or basically shock discontinuity can be modeled. And moving on to the first step, as you know, this equations we solve in CFD are differential equations basically. So as discontinuity occurs, the solution becomes hyperbolic. And the solutions of the differential equations become hyperbolic. So discontinuities are rather becoming difficult to model and change and get the results from. So that's why we chose this topic, and this topic will give an idea is in tandem with the previous topic delivered by Professor Tushar Chaurashi. So let's understand the shock tube problem. So a shock tube, let's begin from the below diagram. A shock tube is classically looks like this. Please follow my laser pointer over here. This thing, there is a driver section and a driven section, and in between them separates a diaphragm. So the driver section is maintained at very high pressure relative to the driven section. The pressure keeps increasing up to a point. It depends on the end user, the what the results you want to be. So in our case, we are setting the driver section to be around 100,000 pascals. I'll discuss more on it. And our driven section is basically around 10,000 pascals. So a huge difference of 10 manifolds. So what happens is, as the pressure builds up, the membrane or the diaphragm over here breaks, and suddenly, what happens is the high pressure enters the low pressure gas area, and there is a contact between these two surfaces. Both the gases are different, and they aren't a reacting mixture. That's a first point to be noted. Usually, the high pressure gas is an inert gas. We either use helium, preferably use helium, but we can also use another air mixture like methane combined with air, which doesn't give out reactions even at a very high temperatures. Because what happens is, when a shock wave is formed, post shockwave, you, as discussed earlier, there is change in temperature, there is change in density, and all the other flow variables. So as and as the flow is progressing, there will be a drastic change in temperature. This drastic change in temperature can facilitate a chemical reaction. So to prevent this, we are using helium. So what are we exactly trying? I'll tell you more on this. As discussed earlier, we are trying to maintain a tandem with the previous lecture. So here in the current simulation, I'm going to focus more on how to implement this using row central form solver in OpenFOAM. What usually happens is, while creating a solution or while setting up a case, it's easy to set up the boundary condition. It's easy to get the mesh relatively. I know many people might disagree, but what is difficult is to obtain a correct solution. Yes, mesh plays the most important role, but if the logic of the solution is not set correctly, you might get a very different altogether kind of solution which doesn't validate the flow physics. Or you might just come and argue why this is happening. So to overcome this, we have to use proper mathematical schemes. Mathematical schemes are basically how are the maths part, the mathematical part, like when you discretize the equations and convert into linear algebra, how they would be solved, what methods would they use, and how the cell to cell approach, how the phase center, cell center, the centroid, this all difficult and different to model approach can be utilized. I believe it's getting little complicated right now, but as you explore the hands-on session more while demonstration, uh, I'll make it more clearer to you. So yes, the challenge is what happens if the schemes, however good, however accurate, they will have spurious oscillations. The spurious relates to the in the visualization. I'll show you very faint lines, which comes along as a part of a fully resolved case. The spurious basically results not intended to, or basically it's a false. It was not supposed to be there. It emerged out of mathematical solving problem, or rather than saying it as a problem, it can say it emerged as a product of solving maths, the maths behind it. The table here represents the different schemes we can apply uh, to the overall case. Both Professor Chandan and Professor Tushar Chaurashi had made it clear the different points: linear, upwind, LUST, TVD, quick, muscle, vanlier, Kurganov, Tadumar. These are all names, and how to implement it depends from case to case basis. I'll teach you how to implement it. The reason, the driving logic needs to be explored case to case basis. Uh, so, as said earlier, I want to show you the diagram of how the case will look like. A current shock tube extends 10-meter in length, and there is just two sections. One is a high pressure, high temperature, relatively high temperature, and vice versa. The red region confines to the low pressure and low temperature region. Okay, and the line separating them is the diaphragm, or a very thin membrane structure. The length is 10 meters and it extends to 2 meters in width. So let's move on to the demonstration part. So this is how the directory should look like. I'll navigate to the each. You can just write tree in the terminal. Okay, after extracting, please open the directory in your terminal. And if anybody is having a problem with extraction or unable to access the file, you can also copy the tutorial case, mention in the tutorial folder using the steps. Just copy KCPR part, just copy the tutorial part. Rest, many things have to be modified accordingly. So please do not follow the rest of the commands as of now. Okay, I'm proceeding. So In the zero, there will be four folders. This is kind of different than we studied initially in the two different cases. uh, we used to see P U T. Okay, here what is the difference part? P dot ORIG. This ORIG or ORIG stands for original. So what happens is each of this file has some values. Okay, and once there is a set fields file in the system. I'll talk about it later. But basically, this originally ORIG files are used to maintain or preserve the original structure. And once we move on to the case ahead, you will see we are generating PTU file, but using some different methodology. And mag of u represents magnitude of u, or the absolute velocity of absolute velocity, which is ux, uy, uz under root whole square of each. Moving on to constant, the usual, the momentum transport and thermophysical properties. The simulation will be laminar, and thermophysical, uh, the usual, the constant. The mixture is air in our case. Prandtl number is 1. I'll delete the polymesh for now. Okay. And moving on to the system part. I'll refer to the comments. 4 files. Yes, we wakes up. You may please clean it using all clean. 4 20 files. Okay, please do not. 4 perfect. Niveda ma'am, dot zone identifier is a common issue while running in WSL. It is basically a harmless file, so you may please ignore it. You can even delete it. It plays no role in the decision factor or running the case. Okay. Moving on to the system. Uh, Please open system folder and let's first go to the block mesh part. Block mesh dictionary. So, as this is a copied tutorial, in the tutorial you would have found the case to be extending in the z direction. This represents x, y, and the z direction. In the original case, it was 1 meter. Okay, I have modified it to 0.5. Anyways, we are not interested in the z direction, so you can model it anyhow, whatsoever the length is. It extends from -5 to +5 as discussed earlier, and the width extends from -1 to +1. Okay. Uh, you might have got cleared about the block mesh basics yesterday when the session from the session conducted by Mr. Evan. And the only thing I would like to bring to your notice is the number of cells in X, Y, and Z direction. In the initial, in the copied case, it was supposed to be 1000 and 1, but I have modified it to 500 in the X direction, 50 in the Y direction, and only one cell in the Z direction, as Z part is not important right now, and the rest part remains same. Moving on to the FV schemes part. Yeah, once again in the tutorial, uh, from the open form tutorial key, there there is no comment key which order of the scheme this is. Yes, there is in the user guides, there is in the muscle memory, but there is no mention. So I've added the comment for the betterment or for well remembering after you, so that the case can be more elaborately understood ki what order schemes are we actually working on. So I'll highlight the flux scheme is the convection part. Like, how are we trying to resolve the convection? Which schemes? So we are using row central form. Row central form has two methods. It's Kurganov and Tadmore. I'll show you both the methods one by one, and you are free to do it on your own as well. Next comes DDT schemes. It's basically how do you want to model the time derivatives, first order, second order. Next come grad schemes, gradient. Deep schemes stands for divergent schemes. Laplacian, it's like how do you want to solve the Laplacian operator part. And interpolation is, assume you have two cells, okay, and you know the value at one center, and you know the value at the center of other cell too. But do you know the values in between? It would be wrong to assume, because the cells would not be strictly rectangular in nature. What if it is triangular? What if it is prism, tetrahedral, or altogether a very quadrangular element? So that's why, how do we model the data in between? So that comes under interpolation. And SN grad schemes is a relative mixture of interpolation and gradient. Okay. As of now, I haven't modified the every schemes part, just added a comment for better understanding, nothing else. Moving on to next, every solution remains intact, no need. Sample can be ignored. And coming to the set fields part. So here we are setting, usually we set the boundary conditions in 0PTU and while defining a mesh. Yeah, this part is important to know what exactly this dictionary is for. Okay, so let's go back to the diagram. Okay, as said right now, I haven't defined a boundary condition for this. Okay, but explicitly I haven't defined, but I'm defining it using the set fields direction dictionary. So what it does is, this red line, this red region, it assigns a value to this red region. Okay, how? You can see the coordinates. Okay, it starts from 0 to 5, and this -1 to 1, and minus 0.5 to 0.5. Okay, so this entire box, and that is the every cell in this region will have a value, and that value is 10,000 for pressure, that is in pascals, 10,000 pascals in of pressure, and 278.746 in temperature. On the other hand, the blue region, that which starts from 000 to the negative part, okay, from here to the left, I'm defining the cell value in a similar fashion, and that is 100,000 pascal and 348 Kelvin, which is approximately equal to 60 or 70 degrees. Okay, that's why the set fields dictionary is very important in our current case. If you want, we can also alter the velocity out here, but that brings out a different continuity issue. So we are not going to delve into it right now, but we can modify. Ha. And one more thing, this is a pressure driven case. So anyways, we have to set the velocity 0. But if you want to see the combination, we can do it if time permits. Um, Closing this. So I'll open in terminal. The simple thing is to dot all run, and everything will do it on its own. But I refrain to use it. We'll go step by step. First comes the block mesh part. Please follow along. Please enter block mesh in your terminal. The block, I entered block mesh. Okay, and the current number of cells which I have, it's 25,000. Okay, if you, if everyone wants, I can increase it to 1 lakh, but yes, the solution time increases, the solving time increases. And please feel free to tinker it on your end, just by changing the block mesh dictionary. The part where I have mentioned 550, only that part needs to be changed. So the total number of cells, as you might have remembered from yesterday, is x into y into z. So in our case, it's 500 into 50 into 1. Okay, that comes out to be 25,000. I'll display you the mesh first. Uniform cells, and just one cell in this layer. And yeah, that's it. Okay. Up if you try to run row central for, I'll tell you what happens. It will give out an error. Any reason? Any input from the user side ki why this give me an error? I have mentioned it in the earlier point, but I would like the users to tell me. Okay. Mr. Arijit, the question was, I did the block mesh part. Uh, I generated it. So after generating the mesh, the usual logic is to run the solver command. Okay, which in our case is row central for. But this gives me an error. I want you to tell me ki what is the point we are missing. Niveda ma'am, we can skip the paraform part for now. It was just to show you the mesh. And I just repeated the question. Anyone with the answer? Like what exactly are we missing? Okay. Yes, Mr. Yogesh, sir. You are absolutely right. Yeah, even Mr. Abhay is right. Set fields. What happens is right now we do not have PTU. OpenForm reads PTU while solving. The first thing which OpenForm reads is P, and it is not there. T is not there. U is not there. So how will a solution progress? So that's why we need to create the P file, the T file, the U file, basically the boundary conditions. And it will be created using the set field directory because we are assigning the field values manually. It's difficult to assign values to each number of cells. Usually what happens is we define a problem, we set the boundary condition. You might be too early to say, you might have seen a problem wherein the values or the field is decided and not the boundary condition. uh, I'll show it from the geometry part. Usually, the starting blue line becomes inlet. This is the walls, no slip adiabatic walls, and this becomes the outlet. But in our case, this is not the case. That's why we are using the set fields to assign a value to the entire region, unlikely to assigning a value to a single edge or a single location. Okay, so we'll enter set fields command. And voila, it creates fields for the entire mesh part. Uh, and now P, T, U are generated. Okay, as you can see, there will be the first line represents the number of cells of the entire mesh and how the values have been assigned. So I think if you navigate to the bottom, and up to the 25,000 line, yeah. So 25,000 values have been entered using the set fields command. Manually, if you would have done, it would have taken eons, no doubt. And remaining things remains ignored. Zero gradient just to ensure that everything happens in a flow. We are not setting anything, but we are allowing the results based on the previous cell. Okay. The T part similarly 348 to a large number of cells. Then in between we find 278 too. So
Pranay,
yeah,
so are you like not setting any boundary conditions and you're using set fields to set the boundary conditions? Is it
yeah,
like that?
yeah. Here in this case, the tutorial case, we do not need the boundary conditions directly, explicitly.
Okay, and what's the reason for that? Can you show it in the PPT?
Yeah. So assume it this way, we want this entire region to be of, to have certain values, right? And this value
Yeah.
to have certain different values.
Mm-hmm.
Okay.
Yeah.
The usual approach when we model something is model inlet, uh, which will say कि the pressure is coming something something something.
Yeah. Yeah.
Yeah, and you would have to define another inlet, but that would basically mean कि what happens at the junction of these two,
Mm-hmm.
and this becomes wall, this becomes wall, and this becomes wall. So there comes reflection from many different points. In this case, the tutorial which has been made, which has been packed in the open form version, we avoid this problem altogether by just setting the field values.
Okay.
Yeah, the field values are basically directing us to, you know, uh, have the value of cell at the zeroth condition predetermined, or not predetermined, but more of a explicitly telling you please set this values and wait for the further instructions कि what values will come post this.
Oh, okay.
Yeah,
Mm-hmm.
it is just a method, it is not कि
Mm-hmm.
this is the only method.
Okay. Yeah.
Yeah, I use this case just to show a different approach can also be done apart from that inlet outlet convention part.
Okay.
Yeah.
Thanks.
I was just saying that the initial setting means that whichever solver like we are using, so it is at the first iteration, right? So at T0 or first iteration, it is starting with that values or like 10,000 Pascals. Then like for all the cells, like 25,000 cells, including the inlet, outlet, like for the high pressure and low pressure regions, for everything it is set to 10,000 Pascals.
Yeah, absolutely. Not everything. The region wise. For the high P part, it is 100,000, and for the low P, that is the red region, it is 10,000. At time equal to zero, the question I understood, the answer you answered your own question, but it, the only different part is this region will have a value of 100K, that is 1 lakh Pascal, and this region will have value of 10,000 Pascal in the beginning. And the reason comes over here, this thing, the fundamental thing of the shock tube is you have to maintain a pressure difference, and that's why there is a pressure difference in the time zero part. Am I clear?
But when you scroll down from top to bottom, na, so it showed for all the 25,000 cells, right?
No,
So
it
that,
didn't, it didn't. I'll show you. See.
okay. Yeah, this is for all the 25,000.
Yeah, this is 10,000. Okay, and see, in between there is 1 lakh 2.
No, I am saying the cell counts. Left side, you see, these are the cell numbers, right?
Right.
These are for all the 25,000 cells. It is assigned 10,000 Pascals.
No, Mr. Ajit. As you can see, this is 10,000 and this is 1 lakh. The numbers are different.
Yes, yes. Okay.
Yeah. I'm clear, right?
Yes, yes.
Yeah. Yeah, it's because of the zeros we usually that didn't strike through. If that is an issue, you can see the temperature part.
Yes, yes, yes.
Yeah, 278, 348. So how that
No.
assigns it depends on its algorithm, but basically it assigns it in such a way that we are able to interpret the region wise. Okay. Before one thing, I missed the control dictionary part, how it is set up. Application row central form, start time, zero time, end time. Okay. So end time. End time is usually shock waves occur at a very small time interval. They can last for long, but the physics is happening at a very small time scale. Okay. That's why our delta t or the time step is 10 raised to minus 6, or that is 1 microsecond. That is the time we are resolving while modeling a shock. We can even go beyond, even lower, but that just adds to the computational expense and is not needed for our current demonstration. Okay. So 0.007, that's like 7 milliseconds. if I'm not wrong, 7 milliseconds. We can resolve our case only up to 7 milliseconds is fine, but I'm resolving it up to 0.02 seconds, so that you can see what happens after a shock propagates and what remains and what can be understood further. Wo- And right interval, cycle right, this is all common and nothing special about this. Uh, we'll come to see this in the visualization part. So let's move on to the solving part.
So after this maze, how did you set this field and how do you generate UV UPT file?
Uh, just enter set fields.
Okay, okay.
Yeah, I'll just set field, and this is the command. Okay,
I have one basic doubt.
yeah, please.
Yeah, like for the set fields, it will assign values for this case only, or it is for the every case we can use the set fields.
We can set it for every case.
But that pressure values and temperature, how it is generated, like 348 kelvins and
Okay, so pressure and temperature in this case was the values that were set previously. We can modify it in this in the set fields value itself. I'll show you. If I change it to 400,
Mhm.
when I generate it,
Yes.
it will be 400. I'll
Okay.
okay. I'll do a part. I'll do this way then. I'll regenerate set fields and so as you might see now, the values which were initially 278 and 348, it's now 400. Okay,
Yes.
and 250. That's how. And in
Okay.
general, for the other cases, you can define it either over here in the internal field. It's for the setting out the entire field. If it is one homogeneous uniform field, you can either set it from the internal field in the PTU file in the zeroth folder. That way you can do without the use of set fields. But if you want another dictionary wherein just like mine the case is split into two different sections and you want to use a set fields dictionary, then you have to define the region, and that region can be defined by explicitly mentioning the geometrical coordinates. Like you have to draw a diagonal and include all the part. uh, as you can see, it starts from 0 -1 0.5 to 5 1 0.5. So a diagonal from one end to the another end of the cube.
Yes.
Yeah, if you want me to change this, I'll change it to, chalo, I'll do it, let's say 2. Every time I modify there, every time I'll have to run the set field. So please ensure ki if you're trying to mimic what I am doing, redo the set fields command every time. It doesn't take time. And now we can start with row central form. So this is the usual solving. It will take some time. Right now we are at 0.002 and will be done. Usually takes 60 seconds on my laptop. Might finish earlier or might finish late on your end. So I request everyone to please run row central form on your terminal. Is it done on your end, sir?
So what's the command again?
It's row central form. Row, RHO,
Hmm.
central, C capital, and FOAM, F capital.
For you, it is showing some execution time of 59 seconds
Yeah.
at the end. For me, it is still running and execution time is
Yeah, if you want to see it, sir, you just drag over your mouse out there if you're on your laptop or anyways, if you're if
132 seconds and it's still running.
yeah, sir. It depends on your computer configurations. Mine is a i7 11 gen, so that's why it is faster. Or if you're on WSL, little slower time does occur. Mine is a dedicated Ubuntu system.
Okay,
So
okay.
yeah, so the time is basically about the computational resources on your workstation, computer, laptop, etc.
So how many computations it will do actually in this?
Uh,
Roughly?
I didn't get exactly like. Are you telling me कि the 25,000 cells के ऊपर कितना calculation होगा कि what exactly?
Yes, 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 yes. Overall, I mean.
Okay, so that is it difficult to see operation because this all operations are floating point operation. The CPU is solving continuously multiplying, dividing, and that happens in millions and billions per second.
Okay, okay.
Yeah, number of algebraic operations is difficult for me to see, but I can quantify the amount कि कितना हो रहा है.
Let me see how long does it take.
What is the command different? Actually, we gave icoform and all, and now it's different. What is the difference?
Okay.
Stand out.
Uh, um. So icoform is a different solver, and row central form is a different solver. So,
Oh, okay,
okay, yeah, we are employing different solvers altogether.
okay,
Row, yeah. And one more thing, wherever we come across a row, that means that case is also a case wherein density is changing at such a path that we have to use compressible fluid mechanics
compressible
process.
flow. Okay.
Yeah.
How will I know that it is moving in the right direction? Suppose it takes 1 hour for me. Suppose then I will be wasting my 1 hour without knowing the things.
So if you are setting up a standalone case, like altogether you just plan to give a case, you have to give a demonstration tomorrow, and you're setting up a case and you have no one to guide around. So that is, it's just hit and trial to come to a conclusion, primarily. Secondarily, usually if try to reduce the number of mesh, right now it is 25,000. See how much time does it take for 2,500 cells. Okay, if it takes
Hmm.
5 minutes, and previously if it used to take 50 minutes, then it's absolutely the number of cells which is causing an issue for a longer time span.
Hmm.
But a standalone, it's difficult to figure out ki how long will it take, because
Actually, why I was asking this question,
Mhm.
there must be some number or some index that I will be watching, and if it is decreasing or increasing, I will be knowing I am in the right direction.
Yeah, sir.
Like that.
Yeah. What happens is, in the terminal, if you can see my terminal, you might be seeing the diagonal for like solving for row, the residual part. Okay, usually all these calculations are very fast, so you have to manually pause on your screen and see. What I usually do is, how do I?
Actually, I will read one block for you. All these values are showing zero. Initial residual zero, final residual zero, number of iteration zero.
Yeah,
But clock time 535 seconds, execution time 245 seconds, delta t 1.04 something, 10 power minus 5.
yeah.
So what does it tell? So anything happening? I have a doubt.
Yeah, in our present context, we are not focusing on the residual part. Primarily, our velocity is zero. There is no change in velocity. The mass is not getting in, the mass is not getting out. That is one thing.
Hmm.
The residual is zero explicitly for this case only, sir. I repeat.
Okay, okay.
Yeah, it is due to the fluid physics. Let me show. Even in the beginning time step, it's a zero. That is the physics governing this case is set up in a such a way that we are not focused on the residual part. But if you want to see the
Okay,
residual,
okay.
you can try the simple form case, wherein Pitts daily case of yesterday. pause on the screen, and you might see the residuals decreasing, the time increasing, residuals decreasing, and after one point, the solution becomes converged.
Okay.
Yeah.
Yeah, mine is done now. After almost 5 minutes, completed.
5 minutes. Okay. So let's move on to the post process right now. I'll show you how the results look like. I'm using the build. Please enter Paraform on your end. I'm using Paraform built-in due to some reasons, because my version of OpenFOAM didn't come along with ParaView. I didn't compile it, so I have to use a native which I have installed manually. So you might just use Paraform, please. Opening Paraform, please click Apply. Okay. For the people who haven't modified the set fields dictionary, you might see a different result. Please keep in mind, you might see a result like this right at the center point. The current set fields that sets a diaphragm at coordinate x equal to 2. In the original file, it's x equal to 0. So please ensure. Uh, I'll show you how the case progresses, then I'll show you the results, how it looks like. Okay. I'll change the color scheme for better post processing. This is the first time step, and this explicitly tells us कि इस region में we are getting a pressure of 10,000, 100,000, and here we are getting a pressure of 10,000. Once the solution progresses, shock is formed at a very high speed. It propagates ahead. So this gray region is marking the presence and the propagation of shock. Shock, as it propagates, brings creates pressure in that region, increases the pressure in that region. So that is what the aim of this case study was, to understand how the pressure is changing, how the velocity, which I'll be doing right now, and the other flow variables change. I'll take rho as of now. I'll once again change a color. You can keep it to anything you like. I usually prefer to have it more color oriented, thoda, for demonstration, so that
Excuse me, how to change the colors?
so please navigate to this corner, to the top left corner, and click edit color map, the second option.
Excuse me.
Yeah, ma'am.
I don't have the row option. I have P, T, and U.
Okay. That's a little strange, ma'am. In the paraform part, are you speaking, ma'am?
Huh, yeah, in the same window, I'm able to see P, U, and T, but not the row, the same step which
Okay.
you are in.
Okay. That's a little strange because I haven't explicitly mentioned row anywhere or altered row. Even in the set fields, the row is not altered. In fact, it's not model only. Um,
How do I enable it exactly?
what comes when you click apply? Like you have applied, right?
Yeah, everything is the
Yeah, yeah.
same.
Then only TUP might have come.
Yeah, everything is the same.
Does MagU come, ma'am?
No,
Magnitude of U is also not coming.
no, I have PTU and the same in box versions and solid colors. That's it.
Okay.
I think from the left side, the cell arrays, she has to click.
for the variables.
Thank you for the solution, ma'am. What comes when you can you look at my mouse, ma'am? I'll navigate.
Oh, okay. I enabled it. I have enabled it.
Yeah.
Okay, okay, okay. Yes. Thank you so much.
Thank you, ma'am. Thank you. Okay. So let's see. Okay. So let's move on to the magnitude of U, or also mag of U, anything whichever you like. I'll show how it looks. Okay. So at time zero, so many of you might have this option, skip zero time. Please click on it and disable it. Yeah. So at time zero, the entire field value is zero. Okay. At first time step, we can see the shock. Okay. Is the shock is forming, and this region which was having a velocity of zero, suddenly at 0.0005 has a velocity of around 240 to 300. The small region around 1 meters, the velocity is changing from 20 to 300 meter per second. This once again happens because there is shock formation and it will propagate ahead. And one thing which I started, or which told in the beginning, is a very faint lines towards the solution part. So if you may see the very faint lines out here, uh, this rectangular ones, one, two, three, four, five. These are those spurious oscillations which I was telling, which comes as a part of solving. Okay, the gradient could have been a smoothly varying, but what happens is dark light. Like, it is very layman to say dark light, but why intend to use that layman term is to highlight the spurious oscillation, the oscillation which is not supposed to be there, but which comes out as a byproduct of solving the equations. I'll come. So yeah, in the beginning it was zero. At time equal to zero, it was the velocity was zero. But as I click on to the next frame, that is at time equal to 5 into 10 raised to minus 4 seconds. That is 0.0005 seconds. I see a increase in velocity, a spike in velocity, a tremendous spike in fact. From zero, it rises up to 300. And that is what the shock waves create. The change in velocity, the change in pressure which we saw earlier, and we will see how temperature and density is changing. So I'll let it run till the end. And I was talking about uh, the oscillations which are part of numerical instability. Need to show you this part. Please, you may please zoom on to this part. There are very thin, faint gradients, and these gradients are what we call as oscillations unintended. But that is for sure gonna come. How much ever you change the scheme, you have to keep iterating, keep what is gonna work. And one find, and it might work for one particular solution. Then you have to change the scheme for another. People doing CFD on daily basis might relate to this, and people who are new to CFD using softwares, uh, but have the mathematical knowledge, can also relate to this. And to overcome this, we have to, yes, once again work on the schemes, or you can just neglect it and do not consider it to be a part of genuine solution, that region, or just add a point of ambiguity or benefit of doubt. You can do anything. But my objective was to show you how the oscillations come in despite having higher order ones. Uh, I'll show you the contours of T and rho in a quick fashion. Then I'll just take a different scheme for one part, if time allows, or else we can wind up the session with the doubt session. Okay, let me apply. I'll take T. So let's move on to the T part, the temperature part. Once again, uh, there will be a change in temperature as the shock wave propagates. The low temperature part will see a increase in temperature, and vice versa for the other part. Anything else? Rho. Yeah. From the contour, you can see the density in the region where shock is formed is less compared to the density in the region where the shock is not formed. This also validates this part of the slide. This image might be a bit small for many of you, but the only intention is to show the density decreases post a shock. And this was about the post processing part. I'll just show you what happens when you
It
yeah.
is not showing a row part. Density option is not showing in the
Yeah.
drop down.
So you need to click cell arrays in the left side of in under the properties tab.
Could you please show me through
Yeah,
your screen?
yeah. So this cell arrays towards the left. Please click on, and then among this you will be able to. Are you done, sir? Were you able to?
Yes, yes.
Yes. Okay. Um, where will you get reflected shocks? Okay. Uh, I'm sorry, sir, but I haven't actually employed the logic of reflected shocks as of now. I understand what that is, but to show you, it's difficult right now. So maybe I'll take it up sometime next, or I can discuss it tomorrow in some free session. Okay. And regarding the results by streamlines, uh, Uh, One of our participants asked about streamline, so I'm just showing her how it happens. Okay. About- So I'll take this plane as of now, ma'am, using the slice command. Okay, and then I'll apply steam tracer on it. Why is it not happening? Yeah, do you? I think I'm missing something about the streamlines part.
Okay, so the streamline part, can you just scroll on top?
Yeah, with
So
this.
first, so first the slice and the streamline tracer, just delete those two.
Mhm. Okay, I'll just delete them. Okay, I'll.
So now with the stream tracer, yeah.
mm,
And instead of line, just scroll on top. Yeah. So instead
Point
of line,
cloud.
just click a point cloud and increase that radius size.
Sure. Thank you.
Yeah. That show spear, just switch it off. So it won't affect.
Okay, it's gonna be fine this way.
Increase it to 1000 or 10,000 will be fine.
Yeah, I'll make it fine.
Yeah.
No, no, no.
You can switch off the spear option.
Okay, switch off the sphere option. Fine. Uh,
This is the second stream tracer you flipped. The first
yeah,
one, I think, you switched it off. Yeah.
I'll just redo it.
Hmm.
I'll have to see.
Increase the radius to 10 and increase the number of points by basically one more order.
Okay. No, I need it on a plane actually.
Let run the simulation, Pranay.
Okay, okay, yeah, yeah. Oh, right. Thank you, Ivan. I need to decrease this. Yeah, I'll decrease the density and maybe then we can see it more much clearer. Okay, Jaspinder ma'am, I think I'll need to work little more on this before I can show you this. Apart from this, do we have any other doubts?
Yeah, I have one doubt, like regarding this density plot.
Mhm.
So if you look at the pressure and temperature contour, what we see at time t0 and first time step, the change is like gradual, right? The
Uh,
pressure temperature is not changing entirely in the entire domain.
mhm.
But if you look at the density at time t0 and the next time step, it is changing suddenly in the entire domain. Is
Uh,
this possible?
no, sir. It is not actually. See, I have the
Hmm?
density right now open.
Yeah, check it
Yeah.
again.
Okay.
From time t is equal to 0 to next time step,
I just read.
just two times time.
Yeah, sure, sure. So this is first time step. Okay.
This is second.
You want
This is not t is equal to 0.
t equal to 0.
Okay, yeah. So
Yeah.
first doubt is why this density is constant in the entire domain where the pressure and temperature are half distributed.
Yeah. So primarily there is no row file over here. Okay.
Yeah,
And secondly, in this, even in the set fields, we haven't explicitly set the density part.
yeah.
That's why at time equal to 0, there is
Mm-hmm.
no density values at all.
Okay,
So what you see a blank screen here, basically at time 0, there is no density value. We
yeah.
haven't defined it at. It is computing density based on what is happening at for future timestamps.
Okay, okay. So it will not affect the solutions, right?
No,
Because
sir.
we need to define it.
Yes, sir. It will not.
Sir, the right word is actually at time step t equal to 0, we are not defining any density gradient actually.
Okay. Noted. Thank you for this, sir.
Yeah, yeah. So, I mean, like there is density. If you can probe, and then there will because our medium is air. What or if we are considering any fluid there. So, dou rho by dou t term will be computed later.
Oh, okay, sir. Thank you for
Yeah,
this. I'll
yeah.
I'll remember.
It is not the pure density. It is the density gradient. Then uh, that is the. I mean, like the shock is the consequence of the density gradient.
Absolutely. Sure, sir. Can you repeat how to plot this results? Sure, ma'am. You would just need to open Paraform, uh, click apply, ensure cell arrays have been like this checkbox has been clicked, apply, select any of the contour value you want to obtain. Maybe it's you. Then run the simulation, ma'am. Any more doubts before we wind up for a tea break?
Yeah, I wanted to ask a question.
Yeah, please.
Uh, you are telling the word cell arrays, right? In
Yes, sir.
my screen, yeah, instead of cell arrays, I get the word fields. Is it same?
Uh, Other option of TU, MAGU, P row.
Yeah, options are T, U, Mag, U, P, row. Yeah, exactly.
Yeah, sir. Then it is.
And above it, it is mass parts and it is under selection, some heading kind of thing.
Uh,
Selection.
okay. And above that, there should be add dimensional units to array names, right? Is it
Add
similar to my
dimensional
screen,
array.
sir? Apart from the naming convention, is it similar to mine thing? As you can see on my screen.
No, that part is not visible. I mean, add dimensional part is not there.
Okay. The upper parts, the top regions.
Yeah, only thing is properties, shock, tube dot form, that is similar. Below it, case, label, those things are different.
Okay, sir. Fine, sir. I'll have to see. Maybe it's a different version of ParaView, or it's actually
Might
different.
be.
Yeah, nothing else. Just the naming different. Or if I don't think that is an issue right now, sir. Like the naming part, just the convention might
Okay.
be different from the
Yeah, you
version.
have 5.11, I have 5.6 paraview.
Yeah, yeah, yeah. I didn't, as said earlier. Actually, I wasn't able to compile it on my system. OpenFOAM 9. It's a source build on my end. That's why I used a native 5.11.
I was asking, can we not plot the results like what you showed in the PPT?
Yeah, we can plot the results, ma'am. I'll
That's what I asked you.
yeah. Okay, I'll show you, ma'am. Just send in my email ID.
Is there any specific reason that you are sticking to version 9 instead of latest version like 24.12?
No, sir, there is no specific version. It's just for the entire FDP workshop, we plan to have OpenForm 9.
Okay, thank
Like,
you.
yeah, just to have continuity and uniformity to every participants, it's 9. Rather than that, I usually use the latest .com version or .org version to run my cases.
Yeah, even in the .org version, the version is right now, I think 12. So open form version 12 has come, and .com version is 2412. So I was just checking that out. Thank you.
Yeah, sir. So this that OpenForm 12 version has modified some solver names. Apart, it has integrated many solvers into one. So you might find less of the solver, little less of the solvers too. You will have to go through the documentation part, ki what has been changed and what has been merged into what. Apart from that, we are good to use both the version as and when required, sir.
Yeah, thank you. Yeah,
Yes, sir. Yeah. And yeah, Niveda ma'am, I'll show you how to plot the results. Yeah,
Yeah, sure.
yeah. So what happens is when you open ParaView, please click on the split button out here, split horizontal axis. Okay,
Okay.
uh, and the line chart view.
Yes. Okay.
Yeah, yeah. And then click plot over. Oh wait, I please close
There
it.
is that option.
Yeah, yeah. Please close that option. Please select plot over line from the top over here.
Hmm. Yeah. Okay.
Okay, then define the coordinates okay, where you want it to. Let's say from 0, from -5 to 5, and I'll take 0 along the axis. Okay,
-5 0 and again 0. What does it mean?
yeah, I'll tell you. So the values will be only for the cells from here to here
Oh,
along the one line.
okay. Along the mid part.
Yeah, along the center line, ma'am.
Okay.
Yeah. If you want, we can also just include 1 minus 1. So what happens now is it it plots values from for the diagonal part.
Oh, okay.
Yeah, it will take the values, all the cells that comes in the diagonal line, all the position, rather we can say the cells that comes in the path of the diagonal line.
Oh, okay. Okay. I'm getting it. I'm getting it.
Yeah,
Yes. Thank you so much.
yeah. To the participants, it was a really delightful exchange of knowledge here. Thank you for being an audience to this host. And I've used some references if for this for preparing out this case setup. You may reach out to me via email. I'll share in the chat box to have this presentation or any future doubts or working on this case. I'll be happy to help and I'll happy to assist anyone, everyone.